Ready to begin?
Ready?
Yep.
Okay. Let's welcome our next speaker for today, Tushar, who will be talking about non-positive curvature and geometry of the whole problem for finitely generated groups. Please welcome.
All right. Thank you, everyone. So today I want to talk to you about a fundamental decision problem in group theory called the word problem. So let's get started. So in 1911, a German mathematician named Max Dehn posed the following problem. This is the word problem. So it says, an element of the group is given as a product of generators. One is required to give a method whereby it may be decided in a finite number of steps whether this element is the identity or not. So this is a decision problem, and when it says decided, it means there exists some algorithm, always terminating, which will tell you whether the word is the identity or not the identity. He also posed the conjugacy problem in the same paper and the isomorphism problem. So the conjugacy problem is defined analogously. Can you tell me in a finite number of steps whether these two words are conjugate elements in a group? So in 1955, the answer to the word problem was found out by Novikov, and they constructed a finitely presented group for which there exists no algorithm to solve the word problem. And this was actually a consequence of the fact that there exists non-recursively enumerable subsets of the natural numbers. So they just took a Turing machine for which the halting problem was undecidable on that non-recursively enumerable set, and then used a group to sort of encode the running of that Turing machine in a clever way, and they found a group where it was undecidable. But mathematicians, they're not easily deterred. They still find groups where they can't solve the word problem. One of them, so Coxeter groups, as you just saw Kieran talk about, braid groups, polycyclic, and non-positively curved groups, which we're going to be seeing today. And quickly we can see here sort of a universe of finitely generated groups here. So I just want to point out that we tend to study these groups that are on the boundaries of this universe. Whereas, for example, the Novikov and Boone group is probably here in the middle. So we need to do a lot more work to understand groups that are in that region. So let's talk about what a Dehn function is. So quickly, we need to know what a free group is. So this a free group is defined on an alphabet. A word in the alphabet is a finite sequence of letters in the alphabet or its inverses. And the elements of a free group are the equivalence classes under free reductions. So we can remove any AA inverse. Group operations concatenation, and for example, this is an unreduced word on the left, and the reduced word is here on the right. I just remove the AA inverse, b squared b, -1 becomes b. Okay. And then the second thing we need to know is presentations. So we've seen many of these during our careers. Another way to define them is, of course, this more abstract way. I have a set and a set of words, so relations, and a surjective homomorphism whose kernel is the normal closure of R. So this just says all the relations become the identity in the group. And the normal closure part is there because the kernel has to be a normal subgroup, it can't just be any set. Okay, so first approaches to the word problem, we can actually quickly identify groups where it is solvable, just using some elementary sort of logic here. So in free groups, we can solve the word problem. This is sort of the most canonical, easy example where we can solve it. That's because if I give you a word in a free group, it's the identity if and only if there's a sequence of free reductions to reduce it to the empty word. So free reductions are just deleting AA inverse. Finite groups, so we can embed any finite group as a subgroup of a symmetric group. And for a symmetric group, you have a cycle decomposition for every element. So you can just check how that acts on your set 1 through n. And that's an easy way to check whether your word is the identity. Of course, products, we just have to check whether it works in the left factor and the right factor, then it's the identity in the product. And we have finitely generated abelian groups and finitely generated subgroups. So we can do more. let's think about the general case. This will work us up to what the Dane function is. So let's say I have a relation decomposed as 3 subwords here, u1, u2, u3. I can apply the relation to replace u2 with u1 inverse and u3 inverse. That's just because this word has to be the identity. I can just multiply by u1 inverse on both sides and right multiply by u3 inverse. So for any word, let's say I have some characters on the left, and then I have u2, and then some characters on the right. You can just take my word that this equality holds. You can just check if you define x1 equals to the left part, and then u1 inverse, you get this. So essentially what we're concluding here is that applying a relator to a word is the same thing as writing it as the product of a conjugate of that relator times like some part of that word. And if we do this again, we're going to get w as a product of 2 conjugates of relators, and then w prime. So what we see here is if a word can be reduced to the empty word by applying n, so capital N relations, and we're going to be able to express it as a product of n conjugates of relators, where the conjugating elements are just any words in the free group, and these are relators. Okay, so now we get to what a Dane function is. So let's see. For a finite presentation, we say that a word is null homotopic if it represents the identity in the group being presented. And if it is a null homotopic word, we define the area of the word. So this is not the Dane function, it's just the area, as the minimum number of relators, so the minimum n, such that we can write it as a product of n conjugates of relations. So it's the minimum such n that we can write it in this form. So given this definition, I just put it back here, the Dane function is, for all null homotopic words with length at most n, it is the maximum area out of all such words. So another way to think about that is it's the maximum number of relations you need to apply to reduce a word to the identity, given as a function of the length of the word. So that's what this n is. Okay, so how do these help us? So for a finitely presented group, we have the following results. So the word problem is solvable if and only if the Dane function is a recursive function, meaning a computable. So in the computability sense, it's recursive, or if it's bounded above by a recursive function. So the intuition for this is that if I have an upper bound on the Dane function, I already know the maximum number of conjugates of relators I need to write my word. So I just need to check all possible conjugates of relations below that upper bound, and then I can see whether the word is the identity or not. Okay, now some quick examples of Dane functions. So this group with just one relator and a to the m as a relation. I'll just check my time. Okay, this group has Dane function the floor of n over m. So a quick way to see that is that any null homotopic word in the cyclic group is going to be some power, so a to the rm, where r is an integer. And this word has length rm, right? A to the rm has length rm. And we're going to have to apply this relation, a to the m equals 1, r times. So rm over r gives us this, in general, this floor function. And then conversely, a to the rm, you need at least r relations, absolute value of r, if r is negative, to transform that word to the identity. And similarly for this presentation, you might recognize that presentation if you've seen it before. If not, that's fine. We have a bound on the Dane function. So it's bounded below by a quadratic n minus 3 squared and above by n squared. And this notation I've written here, we'll see what it means in the next slide because of this problem that we're having right here. So the Dane function of this presentation right here, with a and no relations whatsoever, is going to be 0. Why is it 0? Because any word that's null homotopic can be written as a product of 0 relations, because there are no relations. That's sort of a trivial case there. But you might recognize this second presentation as presenting the same group, right? A, B, and B is a relation. So I just have one relator that's redundant. And the Dane function of this one is n. Because, for example, if I give you the word b to the n, that's going to require n applications of the relation B is equal to 1. So we have the same group presented in two different ways with different Dane functions. So how we remedy this is define equivalence of Dane functions. I guess understanding this specific inequality is not too important. What is important is to know that this equivalence relation on functions, it identifies polynomials of the same degree. So for example, down here, n squared is just equivalent to 15n squared plus 10n. So it's sort of an asymptotic notion of equivalence. And it also identifies constants with linear functions. So that's one sort of quirk of this definition. Constants and linear functions are considered the same, but n squared, n cubed, and n to the fourth, they're all distinct above this. So a few properties down here, of course, and also all exponentials are identified by this equivalence relation. Okay, and of course, we're lucky because that was not actually a real problem, because if two finite presentations define isomorphic groups, then you know that up to this equivalence, the Dane functions are going to be equivalent. So, okay, that's good. So what next? We can ask what functions happen to be Dane functions. This is where we get to the isoparametric spectrum. So let's say we restrict to polynomial Dane functions. So we say a real number alpha is an isoparametric exponent if there exists a finite presentation P whose Dane function is equivalent to x to the alpha. I think this is A, it should be alpha. So the collection of all these exponents that occur as the Dane function of some group is denoted by P, and we call it the isoparametric spectrum. And that comes from the isoparametric problem, which has a geometric interpretation, which we will see why. So first of all, we know that P needs to be a countable subset of 1 to infinity. Why does it need to be countable? Well, there are only countably many finite presentations. So if you just think about, I need a finite set of generators, finite set of relations, that's actually countably many. So the set of exponents must also be countably many, and we can assume it has to be in the range 1 to infinity because the equivalence relation I showed you before identifies constants with linear functions. So we saw that 1 occurs, that was our cyclic group example. We saw that 2 occurs as an isoparametric exponent. That was our Z cross Z presentation. What more can we know? Well, since this theory has developed, we've figured out a few things. So first of all, Gromov here showed that there was a gap between 1 and 2, meaning that if I know that I have an isoparametric exponent that's less than 2, it has to be 1. And this was like a pretty groundbreaking result here. And then eventually people started showing more things about the spectrum. What more can we find out? So later it was proved that there was only one gap, meaning there was no other gaps in the spectrum after 1 to 2. And then all integer values occurs. 3 occurs, that's cubic. And then all non-integral rationals. And then all rationals, and then just more results about this. And then we also have groups with larger Dane functions. So the isoparametric spectrum only restricts to polynomial Dane functions, right? We can have groups that go above. So this group right here is called the Baumslag-Solitar group. And it has an exponential Dane function. And of course, we can generalize that first group to have, okay, these two are out of order. It should be the double exponential here, and then the triple exponential. And we can get groups with much larger Dane function. But it doesn't mean they're always, their word problem is very difficult to solve, because some groups actually have intrinsic structure that makes it easier. For example, the finite groups that I talked about earlier, we can embed them in the symmetric group and use the fact that the symmetric group acts on 1 through n to solve the word problem in finite groups. For example, in this first group I've labeled here, you can recognize it as a subgroup of the homeomorphisms of the real line. And then note that it's isomorphic to the group generated by these two homeomorphisms. And if you do that, you can look at the image of like a single element, like 1/3 under your word, and see whether that is the identity element. Okay, so now I want to motivate what's coming up here. So let's play a game. This is a puzzle kit right here. Okay. So I have 3 puzzle pieces on the side, which you're going to be using. And here are the rules. I have 3 puzzles that I've laid out here, and you have these 3 pieces at the bottom. So your goal is, so you have an infinite supply of these pieces down at the bottom. Your goal is to arrange these pieces at the bottom inside these boundaries for each one, such that the arrows on the outside match the color and the direction of the arrows of the piece. And if you can fill in the entire interior, then you've solved the puzzle. So for these 3 puzzles, there are the solutions. Okay, I just gave it to you. Okay, so you see that you can also collapse edges onto each other, and also the solutions are not unique. So I've given 2 distinct solutions there at the bottom. So why am I introducing this? Well, there's one more thing you can actually do with these completed puzzles, which is once I have a completed puzzle, what I can do is I can take any face intersecting the boundary and I can remove it. Once I remove that face, I can just collapse the edges on the outside, which don't connect to any face, and I can keep removing faces that touch the boundary, and then collapse this diagram all the way down. And this will work for any completed puzzle of this sort. So this is a great analogy for what's coming next, because if I give a label to all these boundary arrows and the colors, so if I label the colors by the letters and I put a direction on them, so opposite direction would be inverse, then what's happening to the boundary label is actually, it's being reduced, so either by free reductions, so that's what happens when, free reduction is when I can remove like A inverse, as I would be removing this green thing here, I think in this step, or I remove a face. And removing a face corresponds to applying a relation. So what we can see here is that a completed puzzle is analogous to what we call a Van Kampen diagram for W. So this is an example of a Van Kampen diagram. So I have a group here, Z to the third, and I have a Van Kampen diagram for this word at the bottom here, this very long word. Okay, doing okay. So you can see that the boundary, if I start at this base point here, and I read around the boundary, it should give me this BA inverse. So B, A inverse, C, A inverse, and then each face in here is a relation of the above group. So each square, let me just choose some square, C, A, C inverse, A inverse. It's some inverse of relation up there. So this is what a Van Kampen diagram is. It is a finite planar contractible 2 complex with edges that are directed and labeled so that around each 2 cells, so that's each face in the interior, I have a relation. And around the boundary of the entire diagram, I have the word that I'm representing as the identity. And what Van Kampen proved, and this is what allows us to use geometry in this subject at all, is these Van Kampen diagrams. So the result here is that a word is the identity in a group if and only if it admits a Van Kampen diagram. And moreover, the area of the word, meaning the number of relators you need to apply to reduce it to the identity, is the minimal faces in a Van Kampen diagram for W. So it's a very useful result here. And of course, this is sort of how it's proved with the technicality sort of stripped away, which is for a word that's the identity, I can represent it as product of conjugates of relations, right? So I can immediately construct this diagram on the left because that's just U are U inverse, U are U inverse, U are U inverse, etc. And if I just morph that a little bit, do some folding, I can get this Van Kampen diagram. Conversely, given a Van Kampen diagram, I can, so I'm just, for the sake of not stating technicalities, you can sort of reverse this process and get back to a product of conjugates and relations and show that that word is the identity. Okay, so let's talk about linear and quadratic Dane functions. So this is sort of where I went in my thesis. So Dane's algorithm is a very efficient way to solve the word problem for many groups. So let's say I have a presentation, a finite presentation, which such that every word that represents the identity for that group presented contains at least one of the words in, let's say, a finite list that I have. And I have a corresponding list such that each word in the second list is shorter. And it's equivalent to the corresponding words in the first list. So what that gives a very easy way to solve the word problem, which is just scan your word for all the elements of the first list and replace it with elements in the second list. That'll reduce the length of the word at least by 1. So in at most the length of W steps, I can reduce any null homotonic word to the identity. So in that way, I can see that any group that has a Dane presentation, so a Dane presentation is a presentation of this form where UI and VI satisfy these conditions up here. And any such group will have a linear Dane function. Okay, so one way we can sort of utilize the geometry in Van Kempen diagrams is small cancellation theory. So, okay, I have to speed up. I might skip this. So essentially, you can, because Van Kempen diagrams are planar, you can use the Euler's formula to deduce certain results about them. So that's what small cancellation theory is. Okay, let's talk a little bit about hyperbolicity. So Gromov came up with a notion of negative curvature, and this is where more geometry comes into play, and this is a global notion. So Gromov's hyperbolicity condition says, given a geodesic triangle, so geodesic is shortest path between 2 points. If I choose 3 pairs of shortest paths, that's a geodesic triangle. It's said to be delta slim if each side lies in the delta neighborhood of the union of the other 2 sides. So you can see here, this side on the left lies inside this, these two, the union of those 2 bubbles. And of course, if every geodesic triangle is delta slim, we say it's a hyperbolic metric space. And we say that a group is hyperbolic if its Cayley graph is delta hyperbolic for some delta greater than 0. So just in case you need to know what a Cayley graph is, there it is. And we can make the Cayley graph into a geodesic metric space by defining each edge to be of length 1, and then the distance between 2 points is the shortest path between them. So one notion here that we have, so the reason that last definition was not ambiguous is because we have a notion of quasi-isometry. Because Cayley graphs depend on their generating set for the group. So you might get different Cayley graphs depending on which generating set you choose, but they're all quasi-isometric. Quasi-isometric, it has this odd-looking condition, but you can think about it pretty simply. So there's a multiplicative factor that the image is off by, so it's just lambda, and there's one sort of scalar, a subtraction or addition factor that you can be off by. So as an example, this lattice right here is quasi-isometric to the plane, the entire plane. And a good way to think about them is if you just squint at this and you try and move as far away as possible, you'll just see the plane. So that's essentially what quasi-isometry does. It ignores the local, sort of what's happening locally. Okay. So for hyperbolic groups, what we know is that Gromov proved that there is a finite Dane presentation. So they all have linear Dane function. And the converse is true as well. Meaning that if I do have a finite Dane presentation or a linear Dane function, then I know my group's hyperbolic. So this is exactly the hyperbolic groups on the S-parametric spectrum. So, and also there's some notion of probability here where you can say almost every group, so most groups you can think of are going to be hyperbolic. Yeah. And then, of course, the reason why this works, this is just what's happening with the Dane presentation here is, let's say you have a path, you can find a path that's sort of not a geodesic. So, for example, let's say this is inside the Cayley graph. Okay, let's talk about cat zero spaces because that's sort of what I go to in my thesis. So let's try to generalize hyperbolic spaces. So what if we say that triangles must be slimmer than triangles in a certain other space? So based on this subscript here, I'm going to vary what that other space is. So for 0, I'm going to say it's the Euclidean R squared space. So cat 0, I'm focusing on comparing triangles to their Euclidean triangles with the same side lengths. So what the cat 0 inequality says, first, if I have a geodesic triangle, I can find a comparison triangle in one of those three spaces I showed you before. That's what this model space is. And such that they have the same side lengths as my original triangle. Okay, comparison points, they're the points of the same side length away from one side. So you'll see on the next slide what I mean by that. What we have the cat K inequality is if for all geodesic triangles, the distance between their points here is less than or equal to the distance between their points in the comparison space. So of course on the left here we have this metric space and their comparison triangle on the right. So we require this distance between x and y to always be less than or equal to this distance between their comparison points. Okay, so quick properties here. We know that they're going to be, geodesics are unique. So if I have like 2 points here, for example, and you're never going to see this, right? Because then like I can find a triangle that's like fatter than its Euclidean counterpart. Also the contractible, right? I can contract each point down to the base point just on its geodesic ray. And we have the metric is convex. Okay, so we define a cat K group to be one that acts properly and co-compactly by isometries on a cat K space. So this is slightly different from hyperbolicity because we can't check it in the Cayley graph. And also, it's no longer invariant under quasi-isometry, so that's, yeah, it's a bit worrying. But I want to get to cube complexes. Okay, so we know that cat -1 groups are hyperbolic. Actually, the converse of this is an open problem still. So we don't know if all hyperbolic groups are cat -1. Similarly, we don't know if all hyperbolic groups are cat 0. And also, we know for cat 0 groups, this is sort of the word for the word problem, they have either linear or quadratic Dane function. So hyperbolic is the linear ones, and cat 0 is not all of the quadratic Dane functions, but it's at least some of them. So the class of quadratic Dane functions can get much wilder than cat 0. And okay, so some examples of cat -1. So -1 just means negative curvature, right? Yeah, so we have these, and also some cat 0 examples. Most notably, this automorphism group of the free group was shown by my supervisor to be cat 0. We also have Coxeter groups, right-angled Artin groups. So many groups are indeed cat 0. And just the last thing I want to touch on is complexes here. So we know Euclidean complexes, so for example, a cell complex is constructed by recursively attaching cells in sort of higher and higher dimensions. We can do the same thing with a cube complex. So if I say all the cells must be isometric to cubes, I can construct a cube complex. And there's an easy way to check if a cube complex satisfies the cat 0 inequality. And that's with Gromov's link condition. And this is probably the last thing I'll leave with, which is the link of a vertex. So we can define the link of any vertex in a cubical complex to be a vertex for every edge incident to that vertex. So you'll see on the next slide what that means. And an edge for every corner of a square at that vertex, a 2 simplex for every cube. So in just higher and higher dimensions, we'll see what the link is. So the link of this vertex, so I have one vertex for every edge incident at V. And then since I have 4 squares attached here, I have an edge connected right here. And same thing for this complex. I have 3 edges and vertices. And this example on the right, we're going to see is not the cat 0 cube complex. But okay, this is sort of the result that I get to in my thesis. This is probably the second last slide, which is Dane functions are actually, sort of didn't mention this earlier, if you pass to a finite index subgroup, the Dane function doesn't change, or at least it's equivalent. So this doesn't work for subgroups, just any subgroups. But you can show actually, even though cat 0 groups have quadratic Dane functions, their subgroups can have arbitrarily large Dane functions. And this uses a lot of heavy machinery. It's called a BRE doubling trick. And it's actually unknown if the exponential function occurs or any non-integral exponent. And I sort of outlined the three-step process in my thesis of how you can do it. So you can show that I have a distorted subgroup. So subgroup distortion is another thing that it's a useful construction by Gromov. Gromov just did a bunch of things here. And we can show that we have a Katsura group. And sort of the doubling trick happens here, which is we can amalgamate two copies of the same group along a certain subgroup. So it's called the amalgamated free product. And if we do this, we know that it embeds in our Katsura group times some free group. And we can essentially construct a subgroup with arbitrarily large Dane function. Okay, and just some implications of the word problem. It implies some other results in about closed manifolds. So it implies the undecidability of the homeomorphism problem for closed manifolds. And of course, moduli spaces in Adrian's talk, and also a crypto system based on undecidability. And yeah, this is the last slide. Just starting with